So I wanted to go through an example illustrating the concept that we just talked about in the last video when we're looking at geometric progression annuities. Take a second to write down the problem, and then we'll get started. Okay, so we have an annuity immediate. We're paying 10 annual payments. The first payment is going to be $100, and each one is 12% more than the previous one. We're going to calculate the present value, assuming that we've got a 4% annual effective interest rate. So looking at our time value diagram, this one's an annuity immediate. We'll notice that in the previous video, when we come up with how to working with these geometric progression formulas, it was an annuity due, but the concept is the same. So the first thing we're going to do, write down our time value diagram. First payment's $100. Since it's an annuity immediate, it's going to occur at the end of the first time period. So we've got that at time 1. Each one goes up by 12% over the previous one. So we multiply that 100 by 1.12 to get the second one, 1.12 squared to get the third one, all the way up to 100 times 1.12 to the 9th to get the last one. And then again, just using our first principles of finding present value, we need to move all of these payments back to time 0. So to do that, we'll take the first one times v. We'll take the second one, and we'll multiply it by v squared. We'll take the third one, multiply by v cubed, and so on up the line, the last one, and we'll multiply it by v to the 10th. Notice that in the previous video, when we were looking at the geometric series, geometric sum, if you will, when we were looking at that, those exponents matched up nicely. In this case, though, they don't. Notice that the exponent on the 1.12 here is always 1 less than the exponent on the v. And that's because, again, in this case, we're doing an immediate annuity rather than a due annuity. But the concept is the same. Remember in that previous video, whenever we had that initial payment of x, we just factored the x out. Notice that every single term in the sum has a v in it. So in addition to factoring out the 100, or the x for this problem, we're going to factor out the v. And then we're left with that nice geometric sum that we had in the previous problem. First payment, or the first term in the sum is 1, second one's 1.12v, third one is 1.12v quantity squared, and so on up the line, so that we notice that that common value of r for every single term is 1.12v. All right? So using our geometric sum formula, we still got this 100v that we factored out hanging out in front. 1 minus r to the 1 higher power, so that's 10 in this case, over 1 minus r. And when we do that computation, we get 1372.75.